Good evening, everyone. My name is Andrew Fracknoy. I'm the astronomy instructor at Foothill College in Los Altos Hills, California. And it's my pleasure to welcome everyone here in the auditorium and everyone listening on the web to the 11th annual Silicon Valley Astronomy Lecture Series. These lectures are co-sponsored by NASA Ames Research Center, one of the premier NASA facilities in the world, in the country, and we're delighted to have the Deputy Associate Director of NASA Ames Research Center here. I'd like to introduce her. That's Yvonne Pendleton. And I want to say how grateful we are to NASA for helping to co-sponsor these programs for 11 years. Another co-sponsor is the SETI Institute, the Search for Extraterrestrial Intelligence Institute, a scientific and educational organization devoted to the search for life elsewhere in the universe. Also sponsoring is the Astronomical Society of the Pacific, a 120-year-old astronomical organization with members all over the world and in all 50 states of the United States, which is devoted to public outreach and education in astronomy. And finally, the astronomy department here at Foothill College is proud to co-sponsor these lectures as well. Tonight's lecture is on a particularly exciting topic, life at the edge, life in extreme environments. And it's my pleasure to introduce our speaker tonight, Dr. Lynn Rothschild. Dr. Rothschild is an astrobiologist, a newly coined word in the scientific literature, but a very exciting field combining astronomy and biology. And she works at NASA Ames, where she specializes in evolutionary microbiology and the use of molecular and cellular techniques to understand DNA damage and photosynthesis in nature. She has gone from the Bolivian Andes to the Rift Valley of Kenya, searching for the most durable organisms in the most extreme environments on Earth. And the idea behind this search is not just to find really strange life forms here, but to think about what kind of life forms might thus be able to exist elsewhere in the universe, and that's what she's going to be talking about. Dr. Rothschild has a degree from Yale, one from Indiana University, and a PhD from Brown University. She's founding co-editor-in-chief of the International Journal in Astrobiology, and she's a consulting professor at Stanford, where she teaches a popular course on astrobiology and space exploration. And she's a wonderful public speaker. She often gives talks to schools and public audiences, and we're delighted at last to have been able to capture her here for Foothill College. So it's a distinct personal pleasure and professional privilege for me to introduce Dr. Lynn Rothschild.
It's an incredibly kind introduction. I must say I speak to a lot of groups. I spoke to 80 eighth graders in Brunswick, Maine on Monday, and I've spoken to audiences all over the world, but I have to say this is probably the craziest audience I've ever spoken to. First of all, you came out on a holiday to listen to someone rant and rave about life in extreme environments. And then if that weren't enough, you sprinted up the north face of Everest to get here. So I particularly would like to extend a warm welcome to all the Sherpas who may want to, sit out front, who carried your luggage up here. All right, well, since I'm a biologist, we have to start with Darwin, and I realize this is the International Astronomical Year, but it's also been a very big year for us biologists. We had a double Darwin year, and many of you, I'm sure, had very large quantities of cake on February 12th because it was Darwin's 200th birthday. I personally baked a several-layer chocolate cake for my class, which went with amazing rapidity. But there's one other little Darwin celebration that we still have coming up, if I can wake my computer back up. This is the last anniversary of the year. Many of you probably have this circled on your calendars. On the 22nd of this month, so in 11 days, is going to be the 150th anniversary of the publication of The Origin of Species. Now, why do we even care? Well, let's go back for a moment from that sort of traditional old man picture of Darwin with the white beard to when he was a good deal younger. Darwin, as you may remember, was somewhat of a diffident student. For the students in the front of the room, it doesn't mean if you do poorly in school you will grow up to be just like Darwin and Einstein. But if you do poorly in school, there's still hope for you. Darwin was not a great student. He ended up going to medical school in Edinburgh. His father sent him there to join his older brother. And remember, this was in the days that they didn't have anesthesia. And somewhere in the middle of the second operation that he had to witness, he said he just couldn't stand it anymore. He ran out, he left, and there was nothing that could make him go back. And he said he had nightmares for years after that. So his father sent him down to Cambridge to study for the clergy. That was not unreasonable for a kid who was interested in natural history, because many people who were in natural history in those days had a little country parsonage. It was a way to understand God's wisdom, not just through his book, but through the natural world around. And at the time, you couldn't even major in science, but he did start to attend lectures on botany and zoology and geology, particularly geology and botany. And at some point after he graduated and took a little field trip with one of the famous geologists there, Adam Sedgwick, his botany professor received a letter asking for a recommendation for a gentleman naturalist to go along on the voyage of the Beagle. Now, this was a voyage that was supposed to be to map the coast of South America, to do some geology work and natural history, and the captain particularly was interested in these things. And so he got this letter through Henslow and asked his father, who is apparently a larger-than-life character, about 300 pounds when he died, very big, and been left with a large family of children. His wife died when Charles was only 9. And he looked at him, and this is the kid, remember, who didn't do well in school, had run out of the second operation at Edinburgh, made it through Cambridge, and now he was saying he wanted to go on a voyage. And he said, I'm not going to let you do this. How many people in the room are parents? This slide is for you. I myself have 2 teenagers, so this really resonates. His father objected strongly, but he said, I'll tell you what, if you can find one reasonable man who can convince me that you should go, I'll let you go. So Charles was very close to his uncle, so he went to his uncle, who said, yeah, I can answer these objections. So these were the objections: that it would be disreputable to his character as a clergyman. It was a wild scheme. They must have offered it to many others. And since the others didn't accept, there must be something seriously wrong. I'd never settle down to a steady life. My accommodations would be uncomfortable, and that is you, Dr. Darwin, that was not unusual in those days to refer to your father, very formally, should consider it as again changing my profession, and that it's a useless undertaking. Well, his uncle answered these questions, and his father sort of teetered on the edge, and Darwin said later in his autobiography that just when he was on the edge, he said, I know I've spent a lot of money at university. He did a lot of hunting and shooting and carousing and drinking, and the sort of things that students do today in university. And so he said, look, I know and this is an exact quote out of his autobiography, I've been rather extravagant at Cambridge, and so to console my father, I said that I should have to be deuced clever to spend more than my allowance whilst on board the Beagle. How can you spend money on a ship? But he answered with a smile, but they all tell me you are very clever. And so he managed to talk his father into going out in the Beagle, and instead of being 6 months or so, it turned into a 5-year journey, and we know what happened after that, that he started to get ideas of a mechanism for evolution, not just that species change, but a mechanism for how that could happen. Now, he was very concerned about whether he had enough evidence, and he was also very concerned about the implications for this. Particularly, he was reminded of this because his wife was very concerned about this. She very much believed in an afterlife, and that this would be going against the Bible and so on, even though she actually was a Unitarian. And at some point later, when he was about 48 years old, one morning at breakfast, he received a letter from a young naturalist who was also taking a voyage, Alfred Wallace. And he said, look, sir, would you please take a look at this idea? He wrote out about a 1-page sketch of exactly the same idea that Darwin had had on natural selection. And you can just imagine your stomach sort of clamping up and churning, because this is something he'd been working on for about 25 years. And he said he didn't know what to do because this other guy had gotten it in print first. Well, he discussed it with some of his close friends, and they arranged to have a joint paper read at the Linnean Society. Here's a picture of the Linnean Society from about that time. It's in London. It's very near Piccadilly Circus, for those of you who've been in that area. I will say, in the spirit of full disclosure, that I am a fellow of the Linnean Society myself, and it looks a little different today in that they now have large portraits of Darwin and Wallace there instead of these other aged gentlemen. The women obviously don't wear those beautiful dresses. But that book there is what you sign when you get inducted as a fellow, and I will say, again, in the spirit of full disclosure, my hand was shaking like a leaf when I signed it. I mean, the thought of signing the same book as Darwin. Anyway, they presented this jointly. They, not Darwin or Wallace, neither of them were there, but it was presented for them. And this is, again, out of Darwin's autobiography, said, our joint productions excited very little attention. The only published notice of them, which I can remember, was by Professor Houghton of Dublin, whose verdict was that all that was new and that was false, and what was true was old. I've had the same sort of criticism myself. It's you know, the refuge of scoundrels. This shows how necessary it is that any new view should be explained at considerable length in order to arouse public attention. And so that's what I'm going to do for the rest of the talk. But just to finish up, The Origin of Species, of course, went on sale the 22nd of November, 1859, 15 shillings, absolute bargain. All 1,250 copies were sold out on the first day. I should add that the publisher had gotten nervous right before it was published and sent it out for peer review and was completely panned. Again, for those of us in the room who are used to having peer reviews that basically say everything from, you know, you're an idiot to your mother wears army boots, Darwin got one of those too. But fortunately, the publisher decided that it was interesting and well worth the publication anyway, and he, of course, never regretted it as it went through 6 editions. So why is it that Darwin is so central to what I'm going to talk about tonight and actually the whole field of astrobiology? Has anyone here read The Origin of Species? Wonderful. And for those of you who haven't, those few who have not read it all the way through, all you really need to do is read the table of contents, which is basically a summary of the whole book. But let me take you through the real meat of it. It's the first 4 chapters that really lay out his idea, and this hopefully will show you why it's so compelling and so important and has been applied to so many different fields besides just evolutionary biology. Well, the first chapter is variation under domestication. And the point of this is simply that if you look at domesticated species, here are just some peppers that I took up in San Francisco at the farmer's market, you see enormous variation. I don't think there is a person here who would argue with this. If you look at the peas at Safeway, you look at dogs, you look at any domesticated species, you see variety. Because if there isn't any variety, there's no point for everyone sitting at Safeway peeling that corn to find the perfect cobs. They are not all the same. So there's variation under domestication. This is a given. Everyone knows that. But the same thing happens in nature. I don't know if you can see, this is a picture I took up in the Bolivian Andes, and you can see that the llamas range from the white to the brown to the black. Somewhere in here I even have a pointer, I think. Yes, yes. There it is. There's some llamas in there. But if you don't believe that there's variation under nature, all you have to do is look at the neighbor sitting next to you. If that neighbor looks exactly like you, I'd be very surprised. When I look out in the audience, there's an enormous variation out there. Okay, so the problem is we got all these organisms, and we're all reproducing at a geometric rate. Not all of us can survive. Not all these flamingos are going to survive to have children. Not every bacterium, not every human. So of all these creatures that are born that there's not enough food for and not enough space on planet Earth, who are the ones who are most likely to have offspring? Well, those that for some reason are better than the others. Now, in the case of this cheetah, he was a little faster maybe than his brother or sister cheetahs, and he's the one who got the impala. On the other hand, this poor impala, which there isn't much of left, must have been a little bit slower, in some way weaker. Maybe his hearing wasn't as good, who knows what. But he was the one who was taken down by the cheetah, and he's not going to have any more kids, that's for darn sure. So that's basically the argument that Darwin made. More born than can survive, and they all have this heritable variability, and the ones that survive are in some way better adapted, and that's how you get this change over time. And the rest of the book really just has to do with difficulties with my theory. He was very, very honest, and other things that might support the theory. So this is what really plays into what I like to think of as the last great scientific revolution, the Astrobiology Revolution. And what that asks is not just how we got the living organisms on planet Earth, but how do we get all the way back to the Big Bang and then forward to the diversity of life on the Earth. So how do we get this history of life? How do we even get the elements that are in our hands? How do we get these biomolecules? How do we get a planet on which to live, and so on and so forth? Are we alone in the universe, or are there potentially other places, other planets or moons that have gone through the same process or similar processes, or perhaps completely different processes? And what is the future of life? What's going to happen downstream to life as the universe ages? So to get at all these questions, the little bit that I tackle is trying to look at what the extremes are of life on planet Earth and use that as a way to get some sort of idea of what the envelope of life might be like, and therefore where it might be worth looking for life elsewhere in our universe. So we need this information to map the limits to life elsewhere, and secondarily to ask this question, would it happen again? Could it happen over and over? Perhaps even it happened over and over on planet Earth. What is there about life that maybe is unique or maybe is not unique? And why do we care? So that sort of gives you a map of what you've got in store for the next half an hour or so. So let's start with why, what their limits of life are. And actually, the first question is really, why are there limits to life? Why can't I walk into a 1,000-degree oven? Why can I not sit in the deep freeze? Why can I not sit in a bath of acid at pH 0? Why can't I sit under a high dose of radiation? Well, the problem is that I, like everyone in this room and every living creature on the Earth, is made out of what we call organic carbon. So this is basically all carbon compounds except carbon dioxide and carbon monoxide and diamond ring, if you happen to be fortunate enough to have one. And I don't, but for those of you who do, diamonds, graphite. My husband's stroking his beard. Nothing personal. I'm just not wearing a diamond ring tonight. Anyway, we're all based on organic carbon. And that's why we have certain limits to life. Because at some point, these carbon molecules are going to break down, whether it's too hot or too much radiation or too cold or whatever. And so that's why we have the limits. But now, why carbon? I'm sure some of you have seen such grade B movies, or C as Evolution, which postulates life based on nitrogen, or various other movies that suggest there could be silicon-based life. But in fact, all the life on Earth is based on carbon. So why carbon? Well, actually, it's the fourth most common element in the universe. And you're sure not going to have life based on hydrogen or helium. So you're way up there. You've got it available. And it turns out it is capable of forming a whole lot of compounds. This enormous diversity from methane, that's a CH4, to DNA, and all sorts of other things from your, stockings to your, plastics to the fat in your body, you name it. Carbon is at the basis of it. It is an incredibly versatile, incredibly clever little atom there. But it turns out that even more than this, and this is something that just stuns me every time I think about it, and again, in the spirit of full disclosure, I was not the world's most brilliant chemist in college, but in fact, our colleagues who do study interstellar chemistry have been able to find compounds based on organic carbon in the interstellar medium. So these are compounds that are not unlike, and some of them, in fact, are identical to the ones in our own bodies. And the ones that they haven't found so far, they've been able to model in the lab when they take chambers that mimic this space, this interstellar medium. And so, as I say to my students, the really scary thing is, if they're students on some planet around Alpha Centauri or, name your star, they may be using the same biochemistry book that we're making our students go through here. I mean, my heart's out to them. But seriously, that there may be a more universal language to life than we could have realized. Not because I don't have any imagination, but because this is really what's out there. So we may be part of this relatively, or perhaps universal, sort of life formula, okay? So the problem is, I mean, this is wonderful. I'm saying, well, all life in the universe is going to be sort of organic carbon, but we only have one field site so far. Now, it's a great field site, and it turns out it's got lots of life on it, as you might imagine. You've got everything from birds to organisms that live at all sorts of extremes of temperature, different levels of pH, whether it's acid or basic, different amounts of radiation, whether we talk about solar radiation or ionizing, different levels of salinity, so in other words, different concentrations of salt, different amounts of desiccation. We are really based on not just organic carbon, but water as a solvent. A lot of our body is water, and this is true of every organism on the Earth. So if you're desiccated, if you're low on water, it's going to be a serious problem as well. There are organisms that live at the chemical extremes. There are ones who live under extremely high pressure at the bottom of the ocean, for example. And I always put electricity in because I wouldn't want to live with an electric eel. I mean, that's got to be an extremophile in there somewhere. So what these organisms that live at these extremes do, once again, is give us an idea what the minimum envelope is for life. Now, I say minimum because if we know that on planet Earth there's an organism that can live at, say, 121 degrees centigrade, which is well over the boiling temperature of water. In fact, basically, it's described as damn hot. That means that if you go to another place, like, say, Venus, and you find some place that's 121 degrees, you say, well, on Earth there's life that can live under these conditions, so it's at least possible that there could be life here. It doesn't mean that there is, but it means that there's nothing per se about 121 degrees that would prohibit life from living there. So what I'm going to do, these are the Olympians. Well, let's say, first of all, I would love to give NASA full credit for coming up with this idea, but Richard Proctor, who is a popularizer of science and I believe an astronomer, British astronomer in the last well, it's no longer the last century, is it? 2 centuries ago, the 19th century, wrote in one of his books, If We Range Over the Earth from the Arctic regions to the torrid zone, don't you love that 19th century prose? We find that none of the peculiarities which mark the several regions of our globe suffice to banish life from its surface, which basically translates to pretty much what I said in the previous slide, that by looking at the range of life on the Earth, we can start to map where it might be possible for life to live elsewhere. So let me give you a couple of examples of these environmental extremes so you can sort of become immersed for a few minutes in this whole idea of thinking of life on the edge, and then we'll try to map some of that onto our neighborhood, our own solar system. Well, temperature, for example, what difference does it make? Well, as I said, since we're based on organic carbon, if you start to get hot, at some point you denature proteins and nucleic acids and so on. And what that means is you're breaking them down. And a very simplistic way to think about it is think about frying an egg. The first thing you do is you put some butter in the pan, and it melts. So you've completely destroyed the structure of those fats. The next thing you do is you break the egg, and that turns from a clear white and sort of a clearish yellow to a very opaque white and opaque yellow. That's because the proteins in that egg are denaturing. They're breaking apart. And if anyone here knows how to put them back together so that you've uncooked your egg, I'd like you to come see me afterwards because we've got a patent here. You know, we're going to make some serious money. The fact is that you've not. You've taken them beyond the temperature that they can survive, and that's all she wrote. And so there should be some temperature that's going to be a limit. The other problem with temperature is that the solubility of gases goes down. And again, if you don't need to believe me, this time instead of frying an egg, take a can of soda, take a can of Pepsi or Coke or Dr. Pepper or whatever. Actually take 2. Put one in the refrigerator and put one under hot water, and then go outside and open both of them. One of them is going to go, and the other one's going to go sort of like that. The one that's going to go kapow is going to be the one that has much less solubility of that gas. And that's going to be the one at the high temperature. So again, when you're at high temperature, you have an issue because you've lost some of the gases that are soluble. And think if you're a fish and you need oxygen and from the water, you're in trouble. Now, there are problems at the other extremes too. What if you're too cold? You can stop the biochemical reactions in your body. You can freeze cell membranes and so on. You know, think about it. It's, you know, no one likes to have a lot of foods once you freeze them and defrost them. They just don't taste right. And the other thing is they just don't have that right, so professor I knew once said, mouthfeel. They sort of taste mushy, and that's because these ice crystals go through the cell membrane. It's sort of like putting a sword through a balloon. So you're breaking the cell membranes, and again, you can't put them back together. So there are all sorts of issues with temperature that are going to prohibit life from living outside a certain boundary. And so you might think from what I've just told you that at the best, life would be able to live from 0 to 100 centigrades. In other words, from freezing to boiling. And this clearly illustrates that there are temperature limits for life. So what are these? I suggested that 0 to 100 might be reasonable, but it turns out we now know of organisms that can live below 0. We know of organisms that literally put antifreeze in their bodies, ones around the Antarctic and also in the temperate regions on the Earth in the winter, so that they're able to buy a few more degrees. They're active down to about -5, -10. There's some organisms that do even better than that. They can go down to -15 or 20. There are bacteria that have been reported to be active that low. I'm not entirely convinced by the data in those papers. I understand the Himalayan midge will bounce around at -17. I've never personally met a Himalayan midge, but again, the Sherpas in the front row maybe can enlighten us later. And of course, we know that the trees sit out there all winter. And furthermore, penguins, seals. There are a lot of organisms that are able to beat these odds. And again, I don't want to offend any of you who might be professional biologists in the room, but before you have a chance to embarrass yourself, I've had colleagues say to me, but they're cheating. They have feathers. Well, you know, gang, there isn't like this book that says, if you break this rule by evolving feathers, you no longer count as living below 0. They've come up with a perfectly good adaptation. You know, give them credit, give them that gold star. So obviously, there are lots of organisms that can live below 0. At the other extreme, it's much more difficult. It's much harder to keep heat out. It's much easier to put on a fur coat or a feather coat or a fat coat. But it turns out that there are organisms that live up by 100 degrees, and in fact, well, up above 100. Now, these are organisms that at this point are bacteria, the eukaryotes like us, drop out right around here. We don't actually do that well, so our cousins, the fungi and the algae and the protozoa and the plants and the animals aren't too good above around in here. We have mostly bacteria, and then this domain of life that looks very much like bacteria, but it's very different biochemically. The archaea are, in fact, the high-temperature champs, and there's some that are up to 121. That doesn't mean that this is hard and fast. And in fact, I'm sure there are people out there right now looking for organisms that can live at even higher temperatures. In fact, if I had done this talk about 30 years ago, the peak you would see would be somewhere in here. By the way, I just have to mention this little Pompeii worm. This is an organism that lives at the bottom of the ocean. And you can see they live in little tubes there. Now, the reason that they're able to beat the odds is sort of the opposite of wearing a fur coat. And I don't want to embarrass the older people in the audience, but a quick show of hands. How many people have seen a Harry Potter movie? It doesn't have, just any one of them. Okay, so when I say Hagrid, you'll know what I'm talking about. And those of you who didn't raise your hand, you'd ask the person next to you. Hagrid is the giant, and he wears very heavy clothes through these movies. And my understanding is that the way he's kept cool, the actor, is exactly the same way the Pompeii worm does. What happens with Hagrid is they run tubing with cold water in it under his coat. I found this out from my children's Discover magazine. The Pompeii worm does exactly the same thing. They have tubes there on the edge of hydrothermal vents. They have tubes sticking out to where it's very cold, and they pump water between their bodies and this tube to keep themselves cool. Life is absolutely amazing. I realize many of you are astronomers, but the fact is that life is amazing. So that's just, I spent a lot of time on the temperature for a reason, because it's easier to relate to. We'll go faster through the other things. Here, this gives you an example of what a high temperature area looks like. This is in Yellowstone National Park, Octopus Springs. If you tilt your head a little bit to the left, it looks a bit like an octopus with legs coming out and so on. This is a really popular place for microbiologists to go. You have a source here that's over 95 degrees centigrade. And because of the altitude in Yellowstone, that's above the boiling temperature of water. And then you start to get these outflows. Here it is about 83 degrees, and it is still extremely hot. I once stepped in it by accident, being very late in the day and very tired, and it is excruciatingly hot. So don't imagine just because it's not 100 that it's cold. But yet you see a lot of these pink filamentous organisms living in there. Unbelievable. When the temperature goes below about 73 or 74 degrees, you can have chlorophyll forming. So here on the edge of this outflow chamber, as soon as it's cooler than about 73 degrees, you see green, you see photosynthetic organisms. And by the time you get down to 65, just to calibrate, that's about where I can stick my hand in extremely briefly. You see a very well-developed microbial mat. It looks a little bit like layered jello, I guess, sort of with cherry and then some kind of bizarre lime jello on top. And here's some micrographs we took of the different organisms that live there. So there are plenty of things that live at these very high temperatures. For those of you who've been to Lassen, you might also have seen some of these organisms that can live at low temperatures. This is in Lassen in July, again. And you may notice that the pink, that the snow is pink. It's a little bit discolored. And that's because there are a lot of green algae on it, Chlamydomonas nivalis in particular. I am not colorblind. These are green algae that have a lot of red pigment to help them deal with the very high amount of solar radiation that they're getting. So here's some in a bag here, and you can see it looks very pink. So these are organisms that do very well right around zero. And as we talked about penguins and so on, there are plenty that can go well below that. So now let's skip through a couple of these other extremes. pH, if you remember from chemistry, that's simply the negative log of the concentration of hydrogen ions. Or to sort of put it in layman's terms, you're talking about a scale going from extremely acidic here to extremely basic. To sort of calibrate this, right now the ocean's just over pH 8. It's about 8.2. We're very worried about it going down below 8 into the 7s in the next 50 to 100 years. Neutral is considered 7. So the insides of our cells are about pH 7. Most of the organisms you know live in this range. But again, there are organisms that can live not just at pH 4 and pH 2. Remember, this is a log scale. So something at pH 2 is living at 10 times an acidic condition as pH 3. But yet there are organisms that can go down to pH 1/2. Here's an organism, Sulfolobus, that lives in boiling acid pots in Yellowstone. Now, the only way you can describe their home is boiling battery acid. Yet these are organisms that cannot live under any other conditions. I mean, just think about that. Organisms that can live in boiling battery acid. I mean, it's outstanding. Yet there are organisms that can even live at lower pH than that. There have been some found basically at pH 0 in California. My guess is we're going to find some below pH 0. And this is not a hard and fast rule. If you start to do the math and the chemistry here, you can see that you can go below pH 0. If you start to go to the other extreme, you don't have very many protons sitting there in the medium. And if you go to some place like the Rift Valley in Kenya or into Tanzania, where we've been several times, you see lakes that are the highest pH lakes in the world, ones that are around pH 9, 10, 11, just over 12. And what you see actually doesn't look too atypical. You see flamingos. Flamingos are tough, if you don't know that. When you see flamingos, you're under harsh conditions. Various people walking around, lots of algae. I don't have a close-up there. Lots of cyanobacteria, nice green, lush growth, few flies, and so on. So there are various odds and ends here from different groups that have managed to live under these very high conditions. So you have not just a range of organisms living in here, but we know on Earth of organisms that can live from pH 0 to about 12, 12.5. Unbelievable. So again, let me show you a quick picture of a place that's only pH 2.5. Now, you're never going to see a pH that's even 2.5 unless you go to someplace like Lassen or Yellowstone or New Zealand or some of these other thermal areas. This is Nymph Creek, nice sort of warm 40 degrees centigrade, but about pH 2.5. There I am actually doing some work. You don't catch that very often. Here's a micrograph. When you're under these very specific conditions, you have almost a pure culture of this red alga, cyanidium, and some fungi in there. Again, I'm not actually colorblind. These are red algae that don't have their red pigment. They just have their chlorophyll, so it looks very green. Salinity. Here's a picture that we took just out in the Cargill salt ponds, the south part of the bay. I'm sure everyone's seen those, at least when you've flown into SFO or into San Jose. Big commercial salt ponds to create salt by evaporation. And what happens is when you go to extremely high salinity, you end up with ponds that look red. Again, many of you may have noticed that flying into one of the airports. You see these red ponds, green and then very red, like this picture here. These are red because the organisms that can live at very, very high salt concentrations tend to have these red pigments, just like the ones that live in the snow. In fact, some of these are archaea, these halophiles, organisms that love salt, and bacteria. There's one that's a eukaryote, Denaliella salina. I happen to work mostly on these eukaryotes, these algae and protozoa. Denaliella salina is very interesting because it also produces glycerol and beta-carotene, so it's used commercially quite a bit, so there's quite a lot of research on it. But there we have these organisms that are in very high salt. And in fact, my husband, Rocco Mancinelli, is sitting there in the audience, has taken some of these with the Europeans and flown them in space on satellites and shown that they could survive in space for some period of time. Now, to show you what happens with different levels of salt, I would like to show you part of the results of a science fair project my daughter Brooke did a couple of years ago, which I think just shows this beautifully. We have a certain salt concentration in our cells. So this is a micrograph of her cheek cells. Just scraped them out, looked under the microscope. So what happens if you put them under high salt? What's going to happen is the water is going to rush out because the cell's trying to keep the concentration of salt the same inside and outside, and now you've left all that salt from the Fritos there, and you can see that they shrunk. And just for, again, full disclosure, this is what happens when you start then drinking water. The cells, you notice, are quite a bit bigger. The nuclei have expanded. And in fact, many of them have already lysed. It was an unbelievable thing to discover. She kept saying, I can't see anything under the microscope after I wash my mouth out with water. And I stupidly doubted her competence. She's an incredibly competent kid. And I said, you're not doing it right. You know, move over, let me look. And in fact, she was doing it absolutely right. What was happening is the cells were bursting. They were bringing in so much water to try to bring down the salinity that they were exploding. And so now I'm wondering if that's why you have a fresh feeling in your mouth when you drink water. That's a complete aside. But anyway, it does show what happens with different salinities. Desiccation is very much related to salinity. Nothing that lives at high salt isn't also resistant to desiccation, losing water. Here's some of these organisms that Rocco flew. This is a salt crust from Baja California. Their biggest salt company in the world is down there, Exportadora de Sal. It's jointly owned by the Mexican government and Mitsubishi. So while Cargill has very large salt ponds, it's nothing compared to what they have down here at ASA. And again, you can see a greenish band in there and some brownish bands. These are organisms that are trapped in this solid salt but seem to be surviving and metabolizing at a very low level, but they're in there and they're active. But there are other ways to be dry. This is up in the Bolivian Andes at about 15,000 feet. There was actually an Inca settlement up there, no longer there thanks to the Spaniards. But you do see many plants that have to go through long periods of time without any precipitation at all. And then what happens, of course, is when they see any moisture, they have to very quickly rehydrate, fix any damage that they've had to their cells, and then do what they need to do, photosynthesize, reproduce, and so on. So these are organisms, again, that live at very low concentrations of water. But there's also things like radiation. We don't tend to think about this. Maybe we think about it a little bit when we hear about skin cancer rates and put on sunblock in the summer and all that sort of stuff. Solar radiation can be very damaging. We tend to live in a very tiny slice of the solar spectrum. Here at the very short wavelengths, you see the gamma rays, X-rays, ultraviolet, then the visible, and this tiny little sliver here, infrared, microwaves, and radio waves. Our world is really this little sliver of the visible wavelengths tiny bit into the infrared and a very tiny bit into the UV. But the fact that we go a little bit into the UV is where the danger comes. And this cartoon just sort of illustrates what I pointed out in a very vivid way. Here we are in the UV, and people worry about it for skin cancer very much. Be very careful in the summer. And the reason that that's so dangerous at UV gets back to the fact that we're based on organic carbon. All of those molecules that go up to make our bodies, the lipids, the fats, in other words, the proteins, the nucleic acids, the DNA, and so on, all of these will break down under UV. And particularly as you start to get to these shorter wavelengths like UVB and certainly UVC, it's extremely dangerous, not just for us, but every living organism on Earth. And as it turns out, that radiation is particularly interesting because it can create mutations as well as select where organisms are. You remember from the origin of species, we're talking about variation and then selection. Well, UV, unlike the salinity and the temperature and the pH that I told you about, does both parts of the equation, so it becomes very interesting. So as you can see, I'm rather interested in that, and so I'm going to give you a very short diversion. Here's an example of why even the UV that we get here in Silicon Valley is so important. This is a simple mind experiment we did with Jackie Gargay, who was a master's student through the International Space University with me about 9 years ago. She went up to the roof at Ames here in Mountain View and took yeast cells, just like you get at the grocery store. This is in March, so it's not even that dramatic a time of year, and started to let them grow either under UV transparent plexiglass that cut out the UVB but let in the UVA, the mylar, and some that didn't let in any UV whatsoever. And you can see very dramatically that even within a few hours, there's an enormous difference in growth rate, depending upon how much UV these guys have gotten. Again, this is March. We all know that March is nothing compared to what we get around here in July, August, and so on. So UV does really control what's going on out there. Now, it turns out that it's more than that. UV radiation can also produce oxygen radicals. Now, we breathe oxygen. That's not so bad. In fact, if we didn't have oxygen near 21%, we're in big trouble. We also take in water. I'm perfectly happy to have a nice big bottle of water. The problem isn't the oxygen or the water. The problem is these compounds in between, these oxygen radicals, particularly this hydroxyl radical. All of them can do really nasty things to our carbon-based chemistry. And not only are we producing these just by living and breathing, but the ultraviolet radiation can produce these oxygen radicals as well. So we have to consider that a very extreme environment as well. Now, I was talking about solar radiation. There's also ionizing radiation. We don't see much of that on the surface of the Earth unless you're in a particular lab where they've got radioactive materials normally. But there are a few places on the Earth that you can see naturally high levels of ionizing radiation. This is Lana Springs, where we took a field trip in the Flinders Ranges in Australia. So it's about a 12-hour or so drive north of Adelaide, if you can picture that in Australia. Now, the first thing you probably notice about this picture are the people in their very cute matching orange shirts and their white hats. Now, the orange shirt people, as my colleague Roberto called them, are from the Beverly uranium mines. It's now part of Heathcote. The uranium mines share some of these aquifers with Lana. And so what you've got is this little pond here that's got uranium in it and thorium. And so you've got little bubbles in there of radioactivity coming up. There's a close-up of the picture of the little bubbles. And yet you can, if you look carefully, you can see floating mats of microorganisms. So somehow these organisms are able to deal with the radioactivity coming up from the bottom, as well as the extremely harsh Australian sun coming from above, which is why the hats and so on. So I've been particularly interested in what life was like on the early Earth, and particularly looking at UV radiation the last 10 or 12 years and so on. So what I've done is try to look where on Earth there might be particularly high radiation. I should add, as an evolutionary biologist, we also are interested because when life arose on the Earth somewhere, well, we know there was life by 3.8 or so billion years. We now have the potential, because of what we learned about the geology of the early Earth, for life much earlier than that, possibly as early as maybe 4.4 billion years. It's an incredible story. So we have possibly for life way back here. Now, if we switch over to this oxygen chart, we can see we already had CO2, so we blocked out the really short-wave radiation. But we didn't get rid of this UV radiation in here until oxygen levels started to rise over time, and not till way up in here. So these organisms, through almost half the history of life on Earth, have had to deal with very high levels of ultraviolet radiation, much higher than we have today. So anytime we're modeling high levels of ultraviolet radiation, we're also going back in time. And this is for those of you who, again, like to see biological intricacies. This is the kind of damage you can see. You can see double-stranded breaks, which we've been measuring, single-stranded breaks in the DNA, which we've also been measuring, the production of modified bases like thymine dimers, which we've also been measuring, and so on. There are a lot of nasty things that can happen to your DNA from the UV. So we look a little bit where it might be highest on Earth today, and I'm sure many of you use similar maps to plan your vacations. We certainly do. These are satellite images reprocessed to tell us where UV's highest. This is January 1st, 2005, and the pink areas are where there's highest UV on the Earth. So that's during the austral summer, so you can see some of Australia, some of Africa, southern Africa, and up here in the Bolivian Altiplano, which is why we were heading up there. If you go into the summer, the northern summer, you see that the Himalayas are the ones that are bright pink. So no matter how bad you may think it is in Mountain View, there are places actually that are even worse in terms of UV radiation. So we go up to the Altiplano, again, because of the high UV, low oxygen, low precipitation, cold, windy, unusual water chemistry. Really intriguing place to be, and I wish I had more time to show you more about it. We've been to Kenya and done some work there. Yes, I happen to have noticed that they're large charismatic mammals, but our excuse was the fact that there were very high levels of UV, and this sort of gives you an idea of what happens when we set up field camp in some of these places. You have this wonderful juxtaposition of doing molecular biology under somewhat primitive lab benches. So no matter what problems you're having at Foothill Andy, there are more primitive lab benches in the world. Actually, that one collapsed shortly thereafter. We were able to say, well, experiments. And we were fortunate enough to talk Scott Parazynski, who just retired from the astronaut corps, into taking some of our experiments up Mount Everest with him. There's Scott looking like an astronaut, and there's Scott looking like a Mount Everest climber last May. Unfortunately, most of the DNA was destroyed, but we do have some solar spectral measurements we're very excited about. And this is, once again, to bring us back to Mountain View, to remind us that you can get huge amounts of variation in DNA damage through the year. These were some experiments I did with my research associate, Dana Rogoff. And here's the amount of damage we're getting in January 2008. This is March, quite a bit higher. September, and then obviously July is substantially higher. And so sort of the take-home message is do wear sunblock when the radiation's high. And again, these other places are even higher. So how could we go even higher on the face of the Earth? Well, we could just try to get rid of some of this ozone layer by going up through it. So we've had a program going on for a while with the Aeronautics and Astronautics Department at Stanford, where we did some high-altitude ballooning. We were able to go up to about 33 or so kilometers, and so we're up through much of the stratospheric ozone layer. And just to give you a feel for what that looks like, well, yeah, sorry, it's sort of like new baby pictures. This was our very first flight where we went from Lick Observatory, balloon burst there, oops, other way around, landed out here somewhere or another. We've also had ones going from Galt, from actually cow pasture in Galt. We've had some going from actually the Casa de Fruta parking lot, if you've been there in Gilroy. That turns out to have been a little bit of a problem because it was owned by a Berkeley alum and it was a Stanford project, but we finessed that a bit. So we're looking for some more money right now to do some more flights, but that's been very exciting because we've been able to bring up organisms up through much of the stratospheric ozone layer, do the measurements. It's really very much of a cheap time travel, and we're hoping to get into some air capture as well. But I promised I'd show you a picture to sort of bring you up to what it looks like. If that isn't space, I don't know what is. Technically, it's near space. I'm sorry about the water drop on the camera, but you can see you're really up over most of the atmospheric ozone layer. It's just, it's amazing. And that was the Pacific Ocean. And it's the sort of results we get. We've been taking, again, the UV spectra. We've been measuring the DNA damage and so on. So what does all of this say about life beyond Earth? Again, no offense to anyone from Iowa, but I love that cartoon. Well, NASA has had a mantra for a while, follow the water. Why water? Because that's the solvent we use for life on Earth. I'm not convinced it's the solvent that we would have to have for life anywhere. I made a very strong argument that we would always have to have organic chemistry, but I'm not sure we'd always have to have water, and there's a reason I'm being a little cagey about that, and you'll see in a moment. So let's just do a very quick tour through the neighborhood and see what all this stuff about extremophiles might mean for life on these different planets. Now, I'm sure you've heard whole lectures on Mars and so on, so I'm going to go very quickly through these rather than dwell for any length of time, but just as a way to start to get you to think about matching the biology with what we know about our solar system. We're going to skip Mercury because Mercury is extremely hot. There is no way that life's going to survive there. On the far side, it's extremely cold. You might think that there's, therefore, this thin strip of prime real estate, but Mercury spins very slowly, so even that's no good. So Mercury pretty much sterilizes itself. So let's forget Mercury and just start with Venus. Now, Venus today is extremely hot. It is the hottest place in the solar system. I know this because I did a television show about it last year. It's, in some ways, our twin that went bad. I mean, it didn't do anything bad. What happened is it got a runaway greenhouse. And so from starting to be like a planet very similar to the young Earth, its greenhouse effect went haywire, and therefore you got this feedback and the temperature went up, 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 up. And so right now the surface of Venus is even hotter than the surface of Mars. It is not a good place to be. My understanding is that the Soviets at one point were sending up a whole lot of missions to the surface of Venus, and some of them had little lead busts of Lenin in them. And so what my understanding is there are now some little lead puddles of Lenin on the surface of Venus. So we go there, we can look for little Lenin puddles. But you will not find any life. It's just too hot. Now, it's possible that there was life that was there before this runaway greenhouse. Unfortunately, it is extremely unlikely we will ever know for sure, but that's an interesting possibility, and I wish we could do some really serious time travel and find out. We do know that there's water vapor in the clouds, and about every 10 years, someone publishes something suggesting that there are organisms that live in the clouds. Now, it's true that you can have organisms that are in the air. We've captured organisms in clouds on the Earth. What's completely unclear is whether these organisms can complete their life cycle or do anything, or whether they just happen to have been lofted up by the currents. We know there's some fungi and some bacteria. My lab's starting to get into that sort of stuff as well. We do know that there aren't any photosynthetic organisms, so where are they getting their lunch from? How do we know they're not photosynthetic? Well, I didn't see any green clouds out there today, or any red clouds, or orange clouds, or any of these other colors that organisms that do photosynthesis are. And again, if someone here is aware of red or green clouds, please come see me afterwards. We got a paper to write. So we don't see big colonies of algae or anything in the clouds on the Earth. But that doesn't mean that it couldn't happen elsewhere, but it does make you feel a little, awkward about this. So it's possible, but we have absolutely no proof. It's possible enough that I think that there's an interest, and there certainly have been missions to Venus, and maybe we'll be able to do a cloud capture. But it'll be a whole lot easier to start doing more cloud capture work on Earth. The next planet that, of course, is of great interest is Mars. Now, I'm not going to spend a lot of time on Mars because many of you probably know a good deal about it, but just to show you a little bit what would happen if we did a parallel between Mars and the Earth through the history of the Earth. So I mentioned the Earth formed down here about 4.5 or so billion years ago, same time Mars did, the rest of the solar system, and we start to see rocks at about 3.8 billion. As I said, there's now a possibility that life could have formed even as much as 4.3, 4.4 billion years ago. We don't know, but we don't start to see really good fossil evidence to about 3.5 to 3.8 billion years ago. Okay, we're way up here. This is just, I put NASA as the pinnacle of all life because I'm paid to do that. But somewhere in the middle here, you see most of the history of the Earth has been dominated by microbes, and then you've got this Cambrian explosion of jellyfish and starfish and dinosaurs and Stanford University and things like that. On the Mars side, however, at this period of time where there was liquid water and so on the face of the Earth, there was most likely liquid water on the surface of Mars. We have all sorts of, they're called geomorphological evidence. You can see what looks like dried deltas and so on, features that look like they formed by liquid water, at the very least underground water going through channels, but apparently it dried. Little Mars wasn't able to hang on to its atmosphere. It got colder and colder, so it's not just the fact that it's farther away from the sun, it's that it doesn't have this atmosphere. And there's always the possibility that there was life forming on Mars, since life arose on the Earth around that time, unless we got life from Mars. But things have not been too great on the surface for many, many years. It's possible that there are organisms living in dried salt, similar to what I showed you a little bit earlier. We know that their salt crust evaporates like the ones we were looking at in Mexico on Mars. So it's quite possible that there's something that survived there. It would have to reproduce now and again, so we're not quite sure how it's getting its water, but it's possible. I didn't say it was likely, but it's possible. It's possible that there's liquid water underneath the surface. We know that there are plenty of organisms that live in aquifers on the Earth. I didn't say it's there. I didn't even say it's likely, but I'm saying from what we know about extremophiles on the Earth, it's possible. It's very depressing that we haven't found organic carbon on the surface of Mars. We think it's sterilizing itself with reactive oxygen species in UV. We don't know for sure. We haven't checked every single inch of Mars. But there are possible places on Mars. This just put this in to remind us that, not so long ago, everybody knew that there were civilizations on Mars. It really wasn't even until the Mariners that we got these depressing photos back. Here's one that gives you an idea of the dried sort of stream bed effect I was talking about. So let's move on to a place that we know has lots of water, and in fact, organic compounds. And this is one of the moons, appropriately Galilean moons of Jupiter, Europa. We think that it's got an iron-nickel core and a liquid water ocean with ice on the crust. And you notice the ice looks really dirty. And we think that that dirty bit is because it's got organic compounds in it. We know that there are these fractures in the ice and that they change so that the crust is moving around quite a bit. And again, we think that there's liquid water underneath the surface. Are there places on Earth that are similar models? Certainly. There are ice-covered lakes in the Antarctic, for one, that are permanently ice-covered, but yet if you go through the ice, if you drill through the ice and go into the water underneath, you see these very lush communities of microbes. And once when I was doing a radio interview, someone in Florida said, oh, but they're simple life. They don't count. And I went totally ballistic. Let me disabuse you of that phrase. There is no such thing as simple life. If you are alive, you are incredibly complex. So whether you're a human, you can pat yourself on the back, but if you're a little bacterium or a ciliate and you can get your flagellum or ciliate around to your little back, pat yourself on the back too. Life is complex. So if you've got microbes at the bottom of that, I would be totally happy. I would be elated. I don't care if they're humans. However, they're obviously not humans under Europa. This rather fanciful picture of a hoped-for mission to Europa where you've got this little sort of hydrobot underneath, you're seeing these hydrothermal vents and things swimming around. Point out once again, this is an artist's rendition. This is not an actual photograph. But we can always live and dream and hope. Moving out from Europa, which, to be honest, I would prefer if, Yvonne, I don't know if we have enough money left in our budget, but if we could swap Europa for Mars, just exchange places, no one would ever notice. We can do it dead of night, no one will ever notice. But I would be much, much happier. But failing that, well, let's take a look at out, see what Saturn has to offer, which is actually even farther than Jupiter. Some of you will remember just a couple of years ago, just about 5 years ago, there was an incredibly exciting mission that touched down on the surface of Titan. Now, why Titan? What's the big excitement? Titan, we were always told before that, is like a frozen chemistry experiment. So I told you that, on the early Earth, you had to have all sorts of carbon chemicals and liquid water that ultimately came together and formed the first life. Well, unlike Mars, there's tons of organic carbon on Titan. And it turns out there's water. It's mostly frozen on the surface, but there could conceivably be liquid water beneath the surface. So we know that it's this huge chemistry experiment. And so what happened was, from the Cassini orbiter, there was this little Huygens probe that was dropped. Again, artist rendition, this is not a photograph. The Huygens probe coming down, and it only was meant to live for a few hours and then touch down the surface. To me, what was so amazing was not just that this was happening, but we were getting results in real time. This was beaming back information. To give you an idea how totally real time, in our world of blogging and everything, real time that this little probe was blogging us. I went to a seminar that afternoon in the geology department at Stanford, and a professor was giving a talk on these results, sitting there with his laptop, basically reading them as they were being beamed back to Earth. I mean, this is just phenomenal. I know some of the kids in the audience will think that, Star Trek and everyone beams around through wormholes all day. But this is not true. This is really amazing stuff. Well, it got to the surface, and I mean, to me, in a way, this is a very disappointing picture for those of us who flew into O'Hare yesterday. This is O'Hare. I mean, you could have taken this landing in the Great Lakes. Doesn't it look like that? I mean, except that Illinois isn't quite this bumpy. It's a little, all you have to do is chop off the hills a little bit, and you got O'Hare. And here's the lakeside there, and the Natural History Museum, and so on. Seriously, you have these large liquid lakes of what we think are possibly ethane, some sort of organic carbon, so not water, because it wouldn't be liquid at that temperature. And then you have these features, including, I don't think I have a picture here, no. What looks like rocks, but they're made out of frozen water. It's ice that is so hard, it looks like rocks. But as I said, we now think that there might even be liquid water beneath the surface. So you have all sorts of potential. And as I told my students the day before this landed, I remember saying that this is fascinating because it's a frozen chemistry experiment, but there's not one person on the Earth that thinks that there's a living organism on Titan. And of course, the next day, one of our wonderful French colleagues said, well, there's a possibility that there's life on Titan. So, this is the great thing about astrobiology. Things may completely change by your midterm or final. But it's an incredibly cool place. And again, it's a little far for weekly trips. It would be wonderful, Yvonne, maybe we can bring that one in a little closer too. Problem is it wouldn't be a frozen chemistry experiment anymore. It would be a defrosted chemistry experiment, but that might be cool as well. So very interesting place, not so easy to get to. Hopefully we'll have more missions there, but don't look in the paper tomorrow because it's going to take a while to get there. Enceladus is the last place I'm going to bring you in the solar system. This is pronounced Enceladus, not enchilada. I've heard it pronounced both ways. This is another little moon of Saturn. This has just come onto our radar screen the last few years. I'd never even heard of it until just a couple of years ago. The reason it became very interesting is that, again, this Cassini orbiter that's going around started sniffing oxygen. It's like, if it were orbiting around this room and sniffed oxygen, it wouldn't be so upset. But you start to go around Saturn, you're sniffing oxygen. It's like, what's going on? And it turns out this was coming from the fact that if you break down water, you get oxygen. And it turns out, and this is a thermal image, false color image, there was a very active region towards the southern part of Enceladus. And what was coming out was liquid, and look at the surface, remind you of Europa? It looks like it was liquid water, and as it came out, it was breaking down into hydrogen and oxygen. That's what was being picked up. So again, you have a body here, another moon that's ice-covered, dark tiger stripes, as the scientists call them, which we think have organic carbon, liquid water beneath the surface. Here's a model of what might be going on, hot rock, pressurized water that's shooting through. Some people call this cold faithful, obviously, to deference to Old Faithful. Again, fascinating possibilities there. So just when you think you know your own neighborhood, we don't even know what's in our own solar system well enough to be able to say for sure whether there's life or not. But none of these places I mentioned to you would definitely be sterile just from what we know on Earth. Every one of them has some kind of analog on Earth, some sort of extremophile on Earth that if we put it there, it could probably live. Now, whether life arose there or not, we don't know. What if we go beyond the Earth? As I'm sure many of you are aware, we've been finding more and more extrasolar planets and probably moons that are revolving around stars other than our own. And what's particularly exciting is that there's a mission that's just gone out, which is being run through NASA Ames Kepler mission, and it's starting to look more and more for these Earth-like planets. Now, it's going to do a fantastic job, I'm sure, but again, let's put this in perspective. Here's the Milky Way. It's going to be a very tiny search space next to the potential in our own galaxy, and of course, there are many, many galaxies out there. So you start to wonder, are we really alone? But there's one other ingredient I forgot to mention. You got to get life started. So just because you've got this chemistry experiment with a lot of organic carbon and you've got water, does that mean that life is going to arise or not? We don't know. No one has actually created life in the test tube yet on the Earth. Now, there are people working on it. So if you see it in the newspaper tomorrow, you don't get your money back for this lecture. I didn't promise you that it wasn't going to happen. But I can just tell you, as of tonight, I am not aware of anyone creating it, and that's working on it specifically. So what are the odds of life originating somewhere else? I don't know. I know it was 100% on the Earth because here we are. But you do start to think, if this is some kind of physical and chemical imperative, at least one of these extrasolar planets or moons must have done something similar to us. Now, one last depressing note. What if we go into the future, that third leg of astrobiology, and look at it? Well, what's going to happen is the moon gets farther away from the Earth, so we start to go into a chaotic obliquity. The tilt of the Earth starts to swing, and we've got more dramatic climate changes. The sun is going to burn hotter and hotter just because that's what stars do, and eventually supernova. So at some point, well before that, the Earth is going to get hotter and hotter. NASA is going to disappear. There's going to be a loss of the oceans. There's going to be death of all life on Earth, and so on and so forth. I was in a show that I think was aired a couple of months ago on the end of life on Earth. It was incredibly, incredibly depressing. You get these another one of those British shows. A lot of these are done by the British and do a wonderful job. But, you pick up the telephone in the morning. It's nighttime for them. And they say, "Excuse me, Dr. Rothschild, just one final question. When is the last insect going to go extinct?" It's like, I haven't even had my morning tea. Well, let's start the day a little more cheerfully. But what I finally said to them, and I insisted they recorded, and of course they cut, so I will say to you, is that I think that we are standing at this period in time somewhere between being in a Greek tragedy where we know all these things will happen and being more optimistic like Dickens was with Scrooge and saying, yes, we know these things will happen if we don't change. But I'm an eternal optimist, and I don't think that we're going to let ourselves be the last to turn off the lights on planet Earth. We're going to work very hard to do something to reset the sun, move the Earth out towards Mars and beyond, spaceship Earth, or something. I don't think if we have the technological capability, we'll just say, oh, sorry, that's all she wrote. Wasn't an interesting experiment. So what are the limits to life? Well, we looked a bit at the limits of temperature, which it turns out were far broader than probably many of you thought before we got into the room. All these things are based on this whole organic carbon idea. There's the temperature graphic. Don't you love Keynote? We've got these extremes in pH, again, much greater than perhaps you knew about before you walked in here tonight. The extremes in radiation, there's organisms that live in the radioactive ponds in Australia, plus ones that are living out in the sun and all these other places. Organisms in solid salt, organisms that can withstand very low water, organisms that can live in chemical extremes. I didn't even mention ones that can do that, like pure CO2 and arsenic and mercury and all these things that I would not try at home. And electricity and pressure, organisms that live at the bottom of the ocean. It goes on and on. So we have a huge envelope for life on Earth. And that envelope is what we now take forward beyond the Earth to give some idea of whether life could live elsewhere. So let's finish up with Darwin. And if we look to his very last paragraph, he says, in The Origin of Species, it's interesting to contemplate an entangled bank clothed with many plants of many kinds, with birds singing in the bushes, with various insects flitting about, and with worms crawling through the damp earth, and to reflect that these elaborately constructed forms, so different from each other and dependent on each other in so complex a manner, have all been produced by laws acting around us. Thus, from the war of nature, from famine and death, the most exalted object which we're capable of conceiving, namely the production of higher animals, well. directly follows. There is grandeur in this view of life, with its several powers having been originally breathed into a few forms or into one, and that whilst this planet has gone cycling on according to the fixed law of gravity, from so simple a beginning, endless forms, most beautiful and most wonderful, have been and are being evolved. But can you imagine how much grander to imagine that this happened in multiple places? So let me just finish by saying, what happens if I'm not right, that there isn't life all over the universe? What if it turns out we are really alone? We need to rethink what we know about the origin of life. It is not then a physical and chemical imperative, because we know the places are there. And if so, we not only change our outlook on science, but I firmly believe we then have to look in at ourselves in a more philosophical way and say, we are really responsible then for our universe, because we are the only living organisms in it with the capability of thought. Again, thank you very much for coming tonight.
If the assumption that the universe has millions of galaxies and billions of solar systems, and then if I ignore for a moment that we are in a random solar system and a random planet, so, and our definition of life is somewhat constrained by temperature and so forth. But if we ignore the constraints, then if we are a random planet, random solar system, then it should be the other way. There is life all over, and we are one of them. If I think as an average layman person, what is your opinion about that?
I guess I was missing what the question was. Yes, probably we're all over. But are you suggesting that we came from somewhere else?
No, I'm saying that it's a high probability that we are not alone.
Right, yeah, I agree with you. And I think some of the best evidence is, I don't know how many of you feel about bankers, but my understanding is that Lloyd's of London stopped taking bets on whether there was life elsewhere a few years ago. So I think, and I certainly wouldn't advise them to take any more bets either.
It's been argued that there may already be life on Mars because they've discovered an organism in NASA's sterilization labs that was able to survive the radiation they used to try to sterilize the probes before they sent the landers over there.
Are you talking about the one on the moon?
I'm not sure which, but anyway, do we have a way to reliably sterilize the probes we're sending to other planets?
No, I think, let me just start with, because I just want to clarify that before someone else asks. There's been an urban legend going around for a while that there was a Cameron surveyor that was brought back to the Earth and it had organisms in it that streptomyces. Okay, good.
No, I'm not referring to that.
I'm glad you don't, okay. But I will finish by saying that for those of you who've heard that, that's not true. It was probably contaminated when it came back. Is there a way to reliably sterilize? The problem is that we, as microbiologists, go into the lab, we autoclave things, there are ways to sterilize. The problem is that the engineers don't want us to autoclave the electronics and so on. And you could do this and have the whole craft melt down. And the other thing is, of course, the cost. And so there's a certain bio-load that we consider tolerable. I wish it were more than that, and I think the assumption is that the rest of the craft becomes sterilized when you go to the surface of someplace like Mars. But I can't guarantee that that's true. It makes me a little bit nervous. So then you're relying, if you find something, on hoping that it's not actually the same as the Earth, because you don't want to say, oh, look, we found life on Mars, and what a surprise. It was the same thing I found in my bowl of Wheaties this morning. You want it to be substantially different so you can prove that it was different. So yeah, we could reliably sterilize it, but it's not probably going to happen. We could probably do better than we are, but can't promise it's going to happen.
Two
I'm
questions.
sorry I don't know all your names. I barely know my own students' names.
Two questions. First one, are there any extremophiles you've found on Earth that could survive on Mars? And the second question is, if not, is there a possibility of combining them and actually create an organism that just could survive on Mars the way Mars is now and perhaps slowly change the environment of Mars?
Great question. On the surface of Mars, you have very high levels of radiation, but it turns out that you could get around that by being under a little bit of salt, like in an evaporite, or you could be under a little bit of dirt or sand, or they call it a Mars regolith, and be protected from the radiation. You would need liquid water at least periodically so that you can do your metabolism and reproduce and fix any damage you're getting. So as long as you get some water periodically, and there are people who think that you do get periodic liquid water beneath the surface, yes, there are organisms on the Earth that could survive on Mars today. I think what you're asking is that could you engineer something with a lot of different resistance? First of all, we already have organisms that are resistant to several extremes. Think about that sulfolobus that I mentioned that's living basically in boiling battery acid. That's living at very low pH and very high temperature. So there are organisms that can do multiple extremes already. There are people in the field of synthetic biology and genetic engineering who are starting to add attributes. I actually have a grad student who I'm working with on similar sorts of projects. One that's been done successfully, not in our lab, but by another group, was taking a gene that was involved with making a product that helped make an organism resistant to losing water and put it in another organism, and it became more desiccation resistant. So that is a direction that we're hoping to go with synthetic biology, is to start to be able to put together organisms and maybe even have it like a tinker set. So you have, a little cubby hole with, here's your gene for low water, here's your gene for low temperature, here's your gene for this, and you land on asteroid X and you put together what you need and pop it into the organism and off he goes. That's sort of the ultimate wild dream. But it may not be such a wild dream. I could see that being ready in another 10 years or so. I forget which side I think I'm on this side.
Hi, I'm interested to know if you or your friends have recreated in a significant chemical detail the conditions on some planet or moon on Earth here in hyperbaric chambers and whatever, and then attempted to actually grow some Earth organisms in these conditions, and if so, which various kinds have been tried?
The only one that I've really been involved in is Mars chambers, and there are a couple of people who have them there. Summit Johnson, the one that we've been using is in, actually it's in southern Indiana. No comment. Anyway, yes, there are organisms that can survive those. Like again, I have a postdoc in my lab who's working on tardigrades, which are water bears. They're little teeny tiny invertebrates that are incredibly resistant when they dry up into what's called the ton state. And so they were able to survive. I know Rocco's had some spores and so on that have been able to survive these Mars conditions. But there's a difference between being able to survive and actually reproducing. So the Mars chambers were at very low pressure and therefore very dry. So there was no liquid water, and so some of these things could survive, but they couldn't metabolize or reproduce. So you'd have to go into a slightly different condition. I've never recreated Europa, but beneath the surface of those ice-covered oceans on places like Europa and Enceladus, I bet you it wouldn't be very hard to recreate. And in fact, we probably have natural analogs in the Earth. We just don't know enough about what the exact salts concentrations are and so on. But we probably already have those analogs naturally occurring. Does that help answer your question? Okay, good. A satisfied customer.
I actually have 3 questions.
Okay.
So, what is Methylpyrus candelaria? Methanopyrus candelaria. You mentioned it in the slide.
Mm-hmm.
Like, what is it?
Do you want to answer that, Rocco?
It's an archaeal methane-producing organism that lives at 113 degrees Celsius.
Did you hear it? No. Okay, it's an organism. It's what's called an archaea. So it looks like a bacterium, but it isn't. And it lives at a very high temperature, 113 degrees centigrade. So that's over the boiling temperature of water. So when you make a cup of coffee or tea or hot chocolate, it's hotter than that water. That's what this organism can live in.
What is a rotifier?
You know what? I can't see the word. I'm sorry. A rotifer. Okay, I'm glad you asked that. A rotifer is a little teeny tiny invertebrate. So they're not unlike if you took a shrimp and shrunk it way down. That's a little bit like what a rotifer would look like. And you have them out in ponds and in the ocean and so on. They're all over the place. But they're little teeny tiny invertebrates. And they're called rotifers because they have a ring of cilia around their mouth that rotates. It spins and helps bring in their food. Okay?
There's actually one more.
All right.
You said tectonics, but not plate tectonics and the Venus slide?
Okay, on Venus, they're tectonics, but they're not plate tectonics. So in other words, the crust is active. Okay, so you can get volcanoes and so on, but not like on the Earth where there are plates moving. You know what? I bet you're going to learn about that in school pretty soon. Okay, let me go on to the next person.
Okay, you said that on Mercury, life couldn't possibly grow because it's so hot. So are you thinking based on the composition of Earth life or just in general any sort of life with any composition?
The problem is if you take any life on Earth and you stick it in an oven at about 500 degrees Celsius, perhaps some of you have tried this in your own oven, you end up with a little pile of carbon. What happens is all the organic carbon breaks down. So if you're going to be on the surface of Venus, which is well above that, no organic molecule, none of your fat, protein, nucleic acids, nothing that goes into making yourself will be able to survive. It'll turn into a little pile of carbon ash. That's why nothing can survive there.
But isn't that sort of thinking based on carbon composition? So could you have life based on different elements and it wouldn't end up like that? Or it could survive being melted? I
don't think you would have life based on another element, but there are other, carbon by itself can survive there. I don't know enough. No one's ever asked me that about silicon chemistry, whether you could have some kind of fancy silicon-based compound that can live can stay intact at those temperatures. Is there a better chemist in the room?
You need a little further back because we get overload.
I'm sorry. I'm apparently getting too close. I should tell a few of you that are left, the only other time I've ever been to the theater was to watch dance performances of the kids. And if I get too far back, I might try to dance. And then you'll really be sorry.
Yeah. I feel kind of silly for asking this, but do you believe that we have been visited by aliens?
Do I believe there have been aliens here?
Yeah.
Well, it's obvious. There was a show of hands before the talk started. There was about a quarter of this room? I just assumed all those people were here to see vacation shots of their home planet. No, I don't believe there are aliens here right now. For a couple of reasons. I don't think that they made the trip, and I think right now we're pretty well covered by Earth life, and so virtually anything that got here would be wiped out pretty quickly. But I don't think we have anything living here right now that isn't part of our whole Earth, Earth life thing. Some people have mentioned the last year that there could be a shadow biosphere. That's not an alien one, but a different origin of life. But every time, and this is really a stunning statistic, every life form that has ever been looked at on the Earth has basically identical biochemistry. They use either DNA, or there are a few viruses that only use RNA. They've got the proteins, they've got the lipids, they've got the same thing. And it's too similar to occur by chance. So all of life on Earth is related. It all had a common origin. Okay?
Okay, we're going to say only people standing now.
Okay, only people standing now, I guess.
Do you believe in global warming, and if so, how would it affect the organisms you were talking about?
Oh, of course. Yeah, global warming.
What would it? Mm-hmm. Yeah, go ahead.
Global warming is certainly occurring. As an evolutionary biologist, if you look back through time, there have been periods much warmer than us. We're actually coming out of a little ice age. If you read all the children's books about, you know, Christmas on, you know, Hans Christian Andersen and all that. Everyone's ice skating down the rivers and so on, and we're not doing that anymore. So it's substantially warmer than it was. It's still a lot cooler than when the dinosaurs were here. And so people say to me, well then, you know, if there are these huge swings in temperature over the last couple of billion years when life was around, why should we care that there's global warming going on right now? There's one big difference. We're here today. Miami wasn't there when the dinosaurs were around. Neither was New York, neither was San Francisco. And very tiny changes in our climate have enormous effects on a large number of people, which we do care very much about. We don't want to see large parts of Africa starve to death. We don't want to see, well, maybe we do want to see Miami go underwater, but there are people in Miami who don't want to. You know, there are people in much of the Earth's population lives near coastal areas. So we have an enormous amount to lose by this, and that's why we're so concerned.
Am I recalling correctly, I heard you say that there are organic compounds found in interstellar space? Is that right?
I'm sorry, I couldn't, you know, there must be some feedback because I'm having a lot of trouble understanding what people are saying.
I'm sorry. Did I hear you correctly? Did you say that there have been organic compounds found in interstellar space?
Yes.
Is there any postulates or theories on how organic compounds would have gotten out there?
Yeah, they're actually formed out there. It's not that they came from the Earth and traveled out there. They actually form out there.
So
just
carbon,
like water forms out in interstellar space and so on.
And carbon is one of the elements just floating around in,
it's
in the medium?
It's the fourth most common element in the universe. It's created, the Big Bang created hydrogen, helium, and a tiny bit of lithium. But everything else basically has gone through the furnace of a star. And so it's come from a supernova of a star burning. That's how you get carbon. And so there's stars all over the place. You get carbon all over the place.
My question is about the limits of radiation that life can tolerate. You didn't give any quantitative limits, like how many rads.
I didn't, and I don't, because I don't think we really have a good handle on it. The organism that's considered the champion on the Earth that we know about is a bacterium called Deinococcus radiodurans. And to give you an idea, it was discovered on some food in the 1950s that had been irradiated to sterilize it. And this organism was still growing. It can withstand enormously high amounts of radiation. But I don't remember the amount of gray specifically off the top of my head. I'm really sorry. You can find that information pretty quickly, though, on the web. But it is, you know, orders of magnitude more than we could survive. That doesn't mean that there aren't organisms that might even be better than Deinococcus. I would love to find, you know, someone to unseat him just because, you know, isn't it fun to knock off the Guinness Book of World Records guy?
Could you repeat that name, Deinococcus?
Deinococcus radiodurans, Deinococcus. Am I close, Rocco? Okay.
Okay, thank you.
And if you can't find it, we'll help you find it.
I guess I'm your final troublemaker for the night. First, a quick comment about the global warming comment that you made. I've heard that the authorities in Europe are making plans in case they have to abandon London and Amsterdam. It's not just Miami, it's actual civilization too.
We won't discuss what goes on in northern Amsterdam.
And you actually, my original question was going to be about whether there was any evidence of existing or formerly existing ancestries that are separate. And you've answered that, but I wanted to ask what, you said no.
Well, no, let me be fair.
Okay.
There may well have been multiple origins of life on the Earth, but the only ones that are surviving today all came from a common ancestor. Right. It's sort of like the Neanderthal situation. There may have been lots of origins of life, and we knocked out the others for whatever reason.
But we haven't seen any.
But not today, I bet you
any evidence of those living or formerly living.
Right. I mean, we're talking about they would have been wiped out, you know, 4 billion years ago.
Right. But the other thing I wanted to ask about, and this may be just beyond any reasonable scope, is if all known life forms can include either DNA or at least RNA, that's an awfully big leap from the amino acids in interstellar space. And I'm just wondering if there's any work going on how you get from here to there.
Right, yeah, and it's not certainly in my lab, but people like Lou Alomandola at NASA Ames has a lab where they have interstellar chemistry chambers to model those conditions and have been able to produce nucleic acids. So they haven't seen them out there yet, but they've modeled their production. Once you have cyanide, I believe you can start to build up to all sorts of really interesting things.
It took time to create them. It'll take
yeah.
us time to find them, too.
And just because we use RNA and DNA doesn't mean that another organism would have to. And in fact, Leslie Orgel, who was one of the great origin of life researchers who passed away a few years ago from San Diego, thought that probably the original genetic material was something like a substituted glycerol, which is a whole lot easier to form a glycerol compound, and that it changed. Over time, Graham Cairn Smith in Glasgow feels that the first sort of template was a clay, which it turns out has crystal structure where you can actually template information. So there are a lot of other things that could originally be used, and then you could take over with something more complicated like DNA or RNA eventually. So you wouldn't even have to start with those. Okay. Wow.
Hey, let's thank Dr. Rothschild. Please. A wonderful introduction to intelligent life on Earth. And thank you all for coming. We'll see you in 2010 for the next lecture.